Okay, hello and welcome to the 6.1 notes for Integrated Math 2, the absolute value function. Before we get started, we are going to do a little bit of a reminder and a review for graphing quadratics. And so you'll see that I've got this titled warm-up, graphing, and then example A is f of x is equal to -2 times parentheses x plus 1 squared and then plus 2. The great thing about a video is that at any time if you feel like you need to pause this and replay something, you absolutely can. So feel free to take advantage of those. First thing first, so in order to graph this, I need to recognize what kind of graph I have. And so I am going to recall that this equation is written in vertex form. And that's the form we're focusing on today because that's what's going to be most helpful when we get into absolute value graphs. All right, I'm going to go ahead and draw a grid here. In anticipation of what this graph is going to look like, I am making my y-axis more negative. As I have a lot of experience graphing, I've gotten better and better at anticipating what kind of coordinate planes I'm going to need. And you will too, as you practice. I need two pieces of information to graph a quadratic. I need to know what is the vertex, because that's going to be my starting point. And I also need to know what effect does A have on my graph. And so in this case, I want my h value. Now remember, the h is always the opposite of whatever I'm adding or subtracting to x. So this is going to be a -1, and then my k value is going to be 2. So -1, 2. Gives me a vertex right here. And an a value of -2 means that this graph is going to open down and it's going to be narrower. So remember that I have this, when I have an a value of 1, like I do for my parent function, I have this 1, 3, 5 pattern. Well, in this problem, I have an a value of -2. So I can multiply all of these by -2 to get a new pattern. Now when I go over 1, I'm going to go down 2, over 1, down 6. And for this graph, 10's not going to fit, and that's okay. Whatever I do to one side, I've got to do to the other. And then to the best of my ability, I am going to draw this parabola, filling my graphing window. And then you have a graph with a vertex of -1, 2. And an a value of -2. I would like you to pause this video and on your own paper, please try to graph this second example right here, this B1 that's given, just so that you can play with the skills a little bit. All right. So bringing back to the front here, the graph for quadratic B, hopefully you graphed it on your own and you can now compare to what I have here. You should have a vertex at +2, -4, which is this location here. And then I have a parabola opening up with my traditional shape and size of a vertical shift of 135. Vertical difference of 135. Okay. And then let's go ahead and jump into our actual notes on the absolute value function. So a reminder about the definition of the absolute value. The absolute value is basically the distance a number is from 0. An example, if I am talking about the absolute value of -11, Negative 11, how far away is that from 0? It is 11 units. Now, distance is always, always, always positive. If somebody asks, how far do you live from the school, you would not say negative 3 miles, right? That's kind of strange. If I take the absolute value of a positive number, I still get positive. And now, let's look at this right here. So here is where I see some mistakes sometimes. It happens. I have negative the absolute value of negative 8. Now, if my absolute value bars were parentheses instead, we would look at this as the opposite of a negative and we would call it a positive. But algebra doesn't work like that. These absolute value bars have a different meaning, and so I've got to take the absolute value of the negative 8 first, which gives me that positive 8 there. And then since I have the negative in front, this is actually going to give me a negative 8. So it's just something to be aware of. The parent function, So we always try to look at the parent function before we jump into more details and transformations of a function, so we can have a really good grasp on what it looks like. The parent function for the family of functions for absolute value looks like f of x equals the absolute value of x. You can see it right here. And what we're going to do on this very first example is I am going to create a table, and we're going to graph from there. So let's look at x and f of x. And we're going to kind of build this one ourselves. So let's pick some values to put into a table, and we'll look at each one of these. All right, so I want to plug in negative 3. What does that look like? That looks like f of negative 3 is equal to the absolute value of negative 3, right? If I plug it into my parent function. The left-hand side, remember, is a notation. This is just telling me f of negative 3 is what I'm doing. I'm evaluating the function at negative 3. The right-hand side is what I want to simplify. So what is the absolute value of negative 3? It is 3. Do the next one. What is the function evaluated at negative 2? Well, when I replace negative 2 in for x, I just get the absolute value of negative 2. How far is negative 2 away from 0? It's just 2. So all I'm really doing is I'm taking the absolute value of my x value. So I'm going to skip showing my work there and kind of work from my head. What is the absolute value of negative 1? It is 1. What is the absolute value of 0? 0. What is the absolute value of positive 1? It's still 1. The absolute value of 2 is 2, and the absolute value of 3 is 3. When I go to graph each one of these, all right, remember I'm doing x first, so I'm going negative 3, and then f of x is 3, so it's going to be up 3. Here's that point. Negative 2, 2. Here's a point. Negative 1, 1 is a point. 0, 0 is a point. 1, 1, 2, 2, and 3, 3. Now, my points don't fill the whole graph, but I want to make sure that I fill the entire window. And I can kind of anticipate exactly what these are going to look like. Make sure that I'm accurate here. An absolute value function is going to be this V shape. It's not a parabola, it's not a U shape like a for a quadratic. It's this sharp V shape where one side has a slope, it comes to the vertex. Turns around, and the other half of the absolute value function has a slope with a negative, right? So if one's positive, the other one's negative. If one's negative, the other's positive. It also has an axis of symmetry, just like a parabola. So through the vertex, I could draw an axis of symmetry. And for the parent function, this axis of symmetry is 0. So kind of just making another comparison from quadratic to absolute value functions. If I look at the vertex form of a quadratic function and I connect that to the absolute value function, you're hopefully going to see that it looks very, very similar. Okay. Couple of differences is the quadratic function has a U shape and the absolute value function has a V shape. For an absolute value function, this A actually, it's not exactly slope because slope is only reserved for lines and this is an absolute value function. So I'm going to put it in quotes, but it is going to represent the rate of change. And I'm going to show you what that looks like. For both of these, though, the vertex is still just HK. And so I can use my prior knowledge of quadratics to help me graph absolute value. And you're going to see when you go on into Math 3 how much knowledge of quadratics is going to help you when graphing a lot of different kinds of functions. So example 1, graph h of x, which is a quadratic, and f of x, which is an absolute value on the same graph. And we're going to look at kind of compare and contrast. How are they different? I'm going to choose to use 2 different colors here. And so you might find that helpful on your paper as well. So let's go ahead, and I think I'm going to do my parabola in purple and my absolute value in red. All right, so when I graph my parabola, I'm going to have a vertex at 3, -2. So I go over 3, down 2. Here's my vertex. I know that that gives me an axis of symmetry. And then for my parabola, I have my 1, 3, 5 pattern. Oh, no, I don't. I have double because of the 2. So instead of the 1, 3, 5 pattern, I'm going to double all of these because then I have an A value of 2. So over 1 up 2, over 1 up 6, and 10's not going to fit. I'll do the same to the other side. All right, there's my parabola. The major way that this is going to differ than the absolute value is the shape of the graph. My parabola is a U. My absolute value is a V. The same location, they have the same vertex. But even though this A value cannot technically be called a slope, I am going to use it kind of like a slope. Now it's going to be a little bit different because it's not going to continue with that same slope, but I'm going to go in the opposite direction. So I know that this this absolute value function opens up because I have a positive A value. And so I'm going to go up 2 over 1, up 2 over 1, up 2 over 1 to fill my window. Now the difference here is that the other side of this is going to have a negative slope. And so I'm going to go the opposite direction and make sure that they match, that they're mirror images of each other, right? If I could use a ruler on my tablet, this would look a lot cleaner. Feel free to use a ruler in your notes. But I get these two graphs. Same A value, but different shape. Same vertex. Same axis of symmetry. Nice visual there. Great. So example 2 asks me to graph 2 times the absolute value of x and the parent function on the same graph. So again, I'm going to use 2 different colors. Let's do this parent function. And then it says find the domain and range for g of x. Okay, so the parent function, you actually have it above. You could copy it. It's a really good idea to memorize what these parent functions look like. So parent function is just going to be f of x is equal to the absolute value of x, which means that it has a vertex at 0, 0. It has a V shape, and each side has a slope of 1 and -1. All right, so I get the parent function. And the only difference with the g of x function is that now I have an a value of 2. And so I am working with 2 sides of the absolute value function that have a slope of 2. And then also -2. All right, we haven't talked about domain and range for absolute value function, but it's just about the same as it is for quadratics. So let's talk about it now. Now we are specifically talking about the domain and range of g of x, which is the one that I have graphed in purple. So for an absolute value function, and I'm talking about domain is what happens to the graph according to x, so left and right. As I look to the left and forever and to the right forever of this graph, it's going to continue on forever and ever and ever and ever. And so my domain is going to be all real numbers, just like it is for a quadratic. And I can write that as -infinity is less than x is less than infinity. Or if I were to write it in interval notation, it would look like -infinity to infinity. The range is similar to a quadratic where it's not all real numbers. If I follow this graph up, 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 it's going to go up forever. But if I look down, 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 down to the graph, it's going to hit this vertex and it's not going to go below it. And so it does have a stopping point here when y is 0. And so my range is going to be that y is greater than or equal to 0 if I write this in inequality notation. It does include 0. It hits that point. Or if we look at interval notation, it would look like from 0 to infinity, but the 0 is going to be included, so it's going to have a square bracket. Let me write a little key for you as we keep talking about domain and range. If I have square brackets are equivalent to having less than or equal to or greater than or equal to. And round parentheses are equivalent to having less than or greater than symbols. So just in case you would like that clearly laid out for you. Example 3, another comparison. Graph g of x and the parent function. So similar to what we did before. And then state the domain and the range. If you feel like you want to give this problem a try, I would absolutely invite you to pause this and go try this problem. Okay, so if you're waiting on me, things that we need to notice about this problem and what makes it different is what does the -1/2, what kind of effect is that going to have on the graph? And so this is still an absolute value function. I can tell by the absolute value bars. The negative is going to cause it to open down, and the 1/2 is going to give me kind of a shallower slope on those sides. So I'm going to graph my parent function first. It's got a vertex at 0, 0, and then the sides have a rate of change of -1 and 1. They meet in a point. And then the g of x function that's provided this time, the negative is going to cause it to open down, so it's going to be a reflection across the x-axis. And then I have a slope of 1/2 instead. So I'm going to rise -1 and run 2. Rise -1, run 2. Rise -1. Now they have the same, these two graphs have the same vertex. But this one has a vertical shrink. Hopefully you can notice it's kind of being squashed down. And then let's talk about the domain and the range for g of x. Okay, so now my function's going a different direction. So how does that change the domain and how does that change the range? Well, it doesn't change the domain at all. The graph still goes to the left forever and to the right forever. And so my domain is still going to be all real numbers. I am going to choose to only put it in interval notation here. And now my range. My range now is going to go up, 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 up until I hit 0, but it's going to go down forever. And so that is going to look like -infinity up to 0. You know, I changed my mind. I'm going to do inequality also for these, just so you can see it. It only takes a few seconds. So my inequality notation for my range would look like y is less than or equal to 0. Great. That's going to do it for the graphing section of our notes. And then example 4 and 5 is more about evaluating and understanding what do points look like on the graph. So example 4 says, is 5, -5 on the graph of y equals absolute value of x. Now notice I switched from f of x to y. That's okay. We kind of go back and forth. I do that so that you see them both. What I want to do in this problem is I want to plug this point in for x, y, and see if it's true. If it's true, then yes, it's a point on the graph. If it's false, then no, it's not a point on the graph. And so I have y, which is -5, and I'm going to set that equal to the absolute value of 5. And I am trying to figure out, is that true? What is the absolute value of 5? Well, the absolute value of any singular number is always positive. And in this case, I have the absolute value of 5 is equal to -5, and that is not true. So this is no. 5, -5 is not on the graph. So it fails. Example 5 I wrote in because I feel like this needed a little further discussion. So let's try another one. Is negative 4, 4 on sorry, I couldn't figure out what letters I was missing there. Is negative 4, 4 on the graph of y equals absolute value of x. So I'm going to do the same thing. All right, so I'm going to plug this in for x, put this in for y. So y is positive 4 is equal to the absolute value of x is negative 4. And I want to know, is that true? Let's think about it. What is the absolute value of negative 4? It is positive 4. That's true. So yes, it is. Then it says, if so, state another point with the same y value. Let's think about this. I have a graph. Looks something like this. I have a point on that graph, negative 4, 4. I'm just eyeballing it. What is another point on that graph with the same y value? So same y value, I copy over here. What would this be? Oh, well, that would be x is positive 4, y is positive 4. So that's the answer we're looking for. So if so, state another point with the same y value. 4, 4 would also be on that graph. You'll see variations of these problems in homework, and actually they end up on state testing too. All right. Great. Thank you so much for tuning in, and I hope you learned a bit about absolute value functions. Have a great day. Bye-bye.